Okay, so it's our great pleasure to have Professor Pavel Etingof from MIT to talk at our seminar today. Professor Etingof has done very influential work in many areas of mathematics, including Lie theory, alpha algebras, and tensor categories, just to name a few. So he's a fellow of the AMS and fellow of the American Academy of Art and Science. And he has received many other honors, including invited speaker at the ICM. So it's really our great honor to have Professor Etingof to give his talk today. So Professor Etingof, please.
Yes, thank you. Actually, my talk at the ICM was in Beijing more than 20 years ago, and that was a very nice visit. Mm-hmm. Of course, Beijing now is completely different than then.
Yeah. But we still hope you have more chances to come to Beijing to visit us.
Yes, hopefully. Okay, so I will talk about my joint work with Kevin Colombier and Victor Ostrich, which is this paper here, and it's coming out in the Annals of Mathematics. So so this will be I will start with the classical applications of our result and then explain. So basically a result, we were able to prove some result in the representation theory of finite groups, which was out of reach before. And I'll explain what the result is and how we proved it and how one can use tensor categories to do so. So, so let's start from a classical setup. So G is going to be a finite group, and P is going to be a prime number. We're going to talk about representations of this group over a field of characteristic P. So the interesting case will be the modular case when P divides the order of the group. This is the situation where the category of representations is not semi-simple. So representations aren't semi-simple, aren't completely reducible. And we'll take a finite dimensional representation V of this group over some algebraically closed field K of characteristic P. And then I can define a certain, I can attach to this V a certain combinatorial invariant in the following way. So I will consider the tensor power V to the n. I will be interested in the number of, so the Krull-Schmidt theorem implies that this tensor power can be decomposed into a direct sum of indecomposable representations in a unique way. And I'm interested in the number of summands, but I'm only going to count summands of dimension coprime to P. So it turns out that in general, it's interesting to have the total number of, say something about the total number of summands or the total number of summands which are not projective. But unfortunately, we cannot say much about those numbers. So I'm going to throw away the summands of dimension divisible by P and keep only those which have dimension coprime to P and look at the number of summands with multiplicities. Now, it is clear that this sequence of numbers satisfies the following inequality. The dn plus m of V is greater than or equal than dn of V times dm of V. Well, this is simply because V to the n plus m is the tensor product of V to the n and V to the m. And if I have a summand in V to the n of dimension coprime to P and a summand in V to the m of dimension coprime to P, let us call them X and Y, then X tensor Y also has dimension coprime to P. And so it must have a summand of dimension coprime to P. And that summand will occur in V to the M times V to the N. And so that proves this inequality. So it's basically very easy. And another thing is that clearly dn of V is at most dimension of V to the N, because clearly every indecomposable summand has dimension at least one. And the total dimension is dimension of V to the N. Now, there is a simple fact from elementary analysis, which is a good exercise for students studying analysis. And it's the following, that if you have a sequence AN of positive numbers, which satisfies this inequality, so this means that it's super multiplicative, and at the same time, this sequence is bounded above by a geometric progression, then root of degree n of AN has a limit, which is a positive real number. And so this so we can define, therefore, what we call the growth dimension d of v, which is the limit when n goes to infinity, dn of v to the power 1 over n. So if it's a fact that if you tensor a representation, indecomposable representation, we will see this later, that if you take an indecomposable representation of dimension divisible by p, well, such representations form a tensor ideal, in the sense that if you tensor it with any representation, then all indecomposable summands will have dimension divisible by p. And for this reason, if we start with a representation whose all summands have dimension divisible by p, then that will be also true for any tensor power. And so the number dn of v will be 0 for all n. So this limit is going to be 0. But apart from that, all these numbers dn of v so if you have at least one summand of dimension non-divisible by p in v, then that will be also the case for v to the n. So these numbers are at least 1, and so you will get a strictly positive number, which is at least 1. So here are some obvious properties. So one property is that d of direct sum is greater or equal than d of the summands, sum of d of v plus w greater or equal than d of v plus d of w. So that's easy to show. So I'm not going to explain this because it's an easy exercise. Also, d of v tensor w is d of v, at least d of v, d of w. Like I said, dimension is 0. D of v is 0 if and only if all indecomposable summands are divisible by p. So such representations will be called negligible. And as I said, they form a tensor ideal. And also, if d of x is bigger than 0, so away from this case, it is at least 1 and at most dimension. And actually, from elementary considerations, one cannot say much more than this. For example, it is not clear what kind of numbers this d of v can be. A priori, it's a real number, at least 1, when it is not 0. But is it an algebraic number? Is it transcendental? What properties does it have? All of that isn't clear at all from the elementary point of view. However, it turns out that using the theory of tensor categories, you can actually say a lot more. And this is the main theorem. So it says that this function d extends to a character of the split Grothendieck ring of representations. Namely, it's the same thing as the green ring. So green ring of the category is, by definition, a ring in which a basis is formed by classes of indecomposables, and the product is determined by the tensor product. So you tensor two indecomposables and you decompose them in a direct sum of indecomposables. And so this, in down-to-earth terms, this means that in fact, those two inequalities that we claimed here are equalities. So d of v plus w is equal to d of v plus d of w, and d of v tensor w is d of v times d of w. So it's a ring homomorphism. And another thing is it tells us exactly what numbers can occur as these dimensions, d of v, growth dimensions. So they are all algebraic of very specific kind. So namely, let q be e to the pi I over p, where p is our prime. So that's the root of unity. And then we have the notion of q analog of a number m. And this is q to the m minus q to the minus m over q minus q inverse, which is q to the m minus 1 plus so on plus q to the 1 minus m. So this is so q to the 1 minus m minus 3 plus so on plus q to 1 minus m. So this is a q number. And so these are complex numbers, real numbers, in fact. Then for every x in our representation category, this d of x is in fact a linear combination of those q numbers with non-negative integer coefficient. And I can take 1 less than or equal to m less than or equal to p over 2, because the q number mq is the same as p minus mq. So they're symmetrical, and so these numbers are sufficient. And so with non-negative integer coefficient. So in particular, it says that for p equal 2 and 3, well, if p equal 2 and 3, this means that m is 1, and so the q number is also 1. So this means that this d of x is always an integer. But for p equal 5, it says that it can be it's an integer plus another integer times the golden ratio, 1 plus square root of 5 over 2, which is the q analog of 2 in for q equal to e to the pi I over 5. And in fact, those irrational dimensions do occur for p equal 5. We can see that easily from the following example, the simplest example. So the simplest case is g equal to z mod 5. It's a group, the simplest example of a group whose order is divisible by 5. And then indecomposable representations of this group correspond to Jordan blocks of sizes 1, 2, 3, 4, 5. Let's take the three-dimensional indecomposable representation. So this is a representation which sends an element 1 of F5 or Z mod 5, which is generator, to the matrix here. And then you can raise it to power n. And it is easy to see that, well, if you tensor J3, if you tensor odd dimensional Jordan blocks, you only can get odd dimensional Jordan blocks. So you're going to get an times J1 plus bn times J3 plus cn times J5. And then we have these tensor product rules that V tensor J1 equals to J3, because V is J3. V times J3 is J1 plus J3 plus J5. And V times J5 actually is 3 copies of J5. So you can check that the first two rules are the same as in characteristic 0, but the third one, in characteristic 0, you would get, for Jordan blocks, you would get J3 plus J5 plus J7, like for representations of SL2. But in characteristic P, you get just 3 J5, because you don't have any. In fact, the characteristic P don't have any blocks bigger than J5. And using these rules, you can write down the following recursive equations: that an plus 1 equals to bn, bn plus 1 equals to an plus bn. And this implies that bn plus 1 equals to bn plus bn minus 1. And that's a Fibonacci recursion. And we know that the Fibonacci numbers grow. So when we compute our d, so dn of v is just an plus bn, which is the same as bn plus 1. We know that Fibonacci numbers grow like 1 plus root of 5 over 2 to the n. So this implies that in this case, d of v is the golden ratio, 1 plus square root of 5 over 2, which is the q analog of 2. In general, in characteristic 5, like I said, you will have this kind of thing. So, so that's the theorem, and I should mention that that in fact it holds more generally. I said for finite groups, but it actually holds for arbitrary groups and then for Lie algebras, and in fact more generally for any affine group or supergroup scheme over K. So that's the classical result that we were able to prove. And are there any questions up to this point? So I will explain how tensor categories can be used to prove this. But before that, are there any questions?
No, it seems so.
Mm-hmm.
No, there's no question so far.
Okay, so now we pass to less elementary part. So I need to explain how to prove this theorem. And the proof is based on the theory of tensor categories. So I will have to recall some basics. So what is a symmetric tensor category? So it's a category C. I will not give a complete definition. I will just remind the ingredients. So we have a category C, which has structures and oops. Oh, yeah. Now it's good. Okay. So we have category C, which has basically structures and properties of the category of finite dimensional representations of a group. So we want to abstract away the group and only keep the properties of the category. So it's going to be, first of all, a k-linear abelian category, where K is our algebraically closed field. So this means that objects, that morphisms between objects X and Y form a vector space over K, and composition of morphisms is bilinear. And abelian means that we have kernels, co-kernels, and images of morphisms, basically. And also zero, direct sums, and so on. We want it to be Artinian, which means that objects have finite length and forms are finite dimensional vector spaces. So every object, so in such a category, we have Jordan-Holder theorem that there is a unique composition series of every object, and Krull-Schmidt theorem that every object is uniquely a direct sum of indecomposables. So those are additive structures. And then we want multiplicative structures. So we want the category to be monoidal, which means we have a tensor product functor. And we have an associativity isomorphism. So it's an associative tensor product. Also the unit object with an appropriate set of axioms, most importantly, the pentagon relation. Now we want the category to be symmetric, which means that there is a map from X tensor Y to Y tensor X, which is functorial in X and Y, and which squares to the identity, and which satisfies hexagon axioms, which I didn't write here. Also, we want it to be rigid, which means that every object has a dual with appropriate rigidity axioms. So this is the multiplicative structure. And then we have to require some kind of distributivity, which is compatibility between additive and multiplicative structures. And this is just a condition that the tensor product is bilinear on morphisms. And finally, there is a mild condition that endomorphisms of the unit is K. In fact, if you don't impose this condition, all you get is direct sums of such things, when endomorphisms of one is a finite direct sum of copies of K. So this is last condition is not really restrictive at all. And of course, since this was obtained by abstracting away the properties and structures of the category of representations of a group, this is the main example. If G is a group, then the category of representations of this group over K finite dimensional representations is a symmetric tensor category. For example, if the group is trivial, then we get the simplest example of a symmetric tensor category, which is the category of finite dimensional vector spaces over K. And more generally, we can take any affine group scheme, which means that we have a commutative Hopf algebra, and we take comodules over this Hopf algebra, so representations of an affine group scheme. Then there is another example which is not of this kind, which is the category of supervector spaces. And this is denoted by Svec K. And this is defined when characteristic of K is not equal to 2. So this is the category of vector spaces graded by Z mod 2. So it's a Z spaces which have the form V0 plus V1. Or equivalently, you can say that these are representations of Z mod 2 because our characteristic is not 2, so it's the same thing. And the only difference is that the symmetry structure, instead of the usual flip, which sends X tensor Y to Y tensor X, it sends X tensor Y to -1 to the degree of X times degree of Y, Y tensor X, if X and Y are homogeneous. So this degree is 0 if X belongs to V0 and 1 if it belongs to V1. So the only change really occurs when both elements belong to V1, when they're both odd, in which case the permutation is supplemented by a minus sign. And so this category, one can show, it's a nice exercise, that this category is not of the previous type. And in fact, this has a generalization. We can consider affine group schemes, but not in the usual sense, but internal to this category. So this means that we can consider commutative Hopf algebras in this category and look at comodules over those Hopf algebras. In fact, we can do something slightly more general, namely, if your group scheme, affine group scheme G, so you can think of, if you have a Hopf algebra O of G, you can think of this supergroup scheme as a functor of points, Grothendieck functor of points. So it attaches to every commutative algebra in this category a group. In particular, we can talk about points of G over K, which are just homomorphisms from this Hopf algebra to the trivial object, to the unit object equipped with the trivial algebra structure. And so this is an ordinary group. And suppose we have an element there which squares to the identity and which acts, so such an element would act by an involution on O of G by conjugation. And suppose that it coincides with the parity operator. This will be called then a parity element. Such an element doesn't always exist, but if it doesn't, then we can adjoin it formally and obtain a slightly larger group where this element is present. And then you can consider the category of representations of G, rep G comma Z. So these are representations on which Z acts by the parity operator. So remember that a representation of G is a supervector space. So in particular, it has a parity operator that acts by 1 on V0 and by -1 on V1. And so we want the Z to act by parity operator. So that's actually, this is the most general thing you can make out of supergroups. And so one says that in fact, these examples can be characterized by purely categorical properties. So we say that a symmetric tensor category is Tannakian if it has a so-called fiber functor, which is a symmetric tensor functor to the category of vector spaces. So what is symmetric tensor functor? It's just a functor that preserves tensor product. And in the category world, that means that it's equipped with a structure called tensor structure that identify f of x tensor f of y with f of x tensor y, and which satisfies some compatibility with associativity morphisms. And so Tannakian category is the category which has such a functor. And in this case, it was proved by Deligne and Milne that this functor is unique. That's not so hard to show. And moreover, we can define a affine group scheme, which is the group scheme of automorphisms of this functor, which preserves the tensor structure. So tensor automorphisms of this functor. And then the category C is reconstructed as the representation category of this affine group scheme. In other words, a Tannakian category is the same thing as the category of representations of an affine group scheme. And this group scheme is uniquely determined by this category up to conjugation through this procedure, which is called Tannakian reconstruction or Tannakian formula. And now there is a similar story for the supergroups. Namely, we call a category super Tannakian when characteristic is not 2. If there exists a fiber functor to from this category to the category of super vector spaces, so that's again a symmetric tensor functor. So it's supposed to be monoidal. So tensor functor means that it's preserves tensor product, and it's supposed to be exact also. So so that's what we mean by fiber functor. Maybe I should mention that it is supposed to be exact. Exact symmetric tensor functor. And in this case, you can also show that it is unique. So this was also done by Deligne. And you can consider the group of tensor automorphisms of F. That's now a supergroup scheme, affine supergroup scheme over K. And it has a parity. This supergroup has a distinguished element Z, which is well, it's an automorphism of F, which acts on every supervector space F of X by the parity operator. And so that gives us distinguished element of this group. And we can look at the category of representations. This element acts on the group by parity. That's easy to check. And we can consider representation category of this group with this element acting by parity. And this recovers category C. So every category C with such a fiber functor is as this form and vice versa. And moreover, if I give you C, then you can recover this pair GZ up to uniquely up to conjugation. And one may ask if these are all the examples one can come up with. And well, so not quite. There is another condition that these categories satisfy and a general category doesn't. Namely, this definition is also due to Deligne. So a symmetric tensor category C is said to have moderate growth if every object X in C so admits a positive number Cx, such that the length of the composition series of x to the n is dominated by this constant cx to the power n. So the length, if the length of x to the n grows at most exponentially. In fact, it cannot grow usually more slowly than exponentially, but at most exponentially. And so if you have representation category, then such Cx obviously exists. You can simply take the dimension of X over your field. So this category is of moderate growth, but there are some categories that have faster growth, the so-called Deligne categories, rep GLT, which are obtained by interpolation of representation category of the general linear group to non-integer values of T. And there are some similar categories for symmetric group and so on, and they don't have moderate growth, and they are therefore not of this form. But let's disallow such categories and focus only on categories of moderate growth. So we may ask if there are any new examples. And in characteristic 0, the answer is no. And this is the celebrated theorem of Deligne, which says that from 2002, which says that a symmetric tensor category over K of characteristic 0 is super-Tanakian if and only if it is of moderate growth. So of course, one implication is trivial. A super-Tanakian category does have moderate growth for trivial reasons, but the converse implication, this implication is pretty deep, and that's the content of Deligne's theorem. Now, this theorem fails in characteristic P. And it is the failure of this theorem that somehow leads to those irrational numbers, d of v, that we have discussed. And so, in fact, it fails, but we can, but it can be corrected. And this way to correct this theorem has to do with how we prove these classical results about growth of tensor powers. I should mention that in characteristic 2, when I talk about super-Tanakian categories, I really will mean Tanakian, because in characteristic 2, we don't have signs, and there is no difference between super-Tanakian and Tanakian. So now I will explain how this theorem fails in characteristic P and how it can be fixed and how this can be used to prove our main theorem. So any questions up to this point?
No, so far so good.
All right. So so to show that, give a counterexample to Deligne's theorem in characteristic P, we need the notion of semi-simplification, which will also be used for proving our main result. So semi-simplification of a symmetric tensor category. So in fact, we don't need to work with abelian categories. We can consider just additive rigid symmetric monoidal categories. We don't necessarily have kernels, co-kernels, and images. We only have, well, we can take a Karoubian completion, which means we can just adjoin images of split morphisms. So suppose endomorphisms of 1 equals to k. So in this situation, whenever you have a morphism from x to itself for some object x, then we can define the trace of this object, of this morphism, which is a number in our ground field. And this is done in the following way. So recall that I assume that my category is rigid, which means it has functor of dualization, x goes to x star. And this comes with a so-called evaluation and co-evaluation morphisms. So there is a map from 1 to x tensor x dual, which is called co-evaluation. And we have also a map from x dual tensor x to 1, which is called evaluation. And if we are in the category of vector spaces, these are the usual canonical maps. Now, if you have a morphism from x to itself, then you can tensor it with the identity morphism and get a morphism from x tensor x dual to x tensor x dual. And then we can post-compose it with C, which is the permutation morphism, the symmetry morphism, from x tensor x dual to x dual tensor x. And so we can take this composition, which is a morphism from the unit to itself, and we assume that the maps from the unit to itself is the field K. So the composition is going to be a number, which is called the trace of F. And in particular, we can define the dimension of X. This is different from the previous kind of growth dimension. That's called categorical dimension. And that's an element that's not a real number, but it's an element of our ground field. And this is defined to be the trace of the identity morphism of X. And so we define, so now we need an important notion of negligible morphism. So a morphism between two objects X and Y is called negligible if for every morphism G the other way from Y to X, trace of the composition is 0. By the way, it is easy to see that trace of composition FG coincides with the trace of GF, so it doesn't matter in what order we write them. And the first important lemma is that such morphisms form what is called a tensor ideal. It's not the, so I talked already about tensor ideals formed by negligible representations. So that's what is called thick tensor ideal, which means it's defined by a set of objects. But this is a more general notion of tensor ideal. It's a tensor ideal of morphisms. And by this, I mean that for every object X and Y, in the space of morphisms from X to Y, we have a subspace N of XY. And so it's a system of subspaces, and it is supposed to be closed under composition and under tensor product with any morphism. Composition with any morphism and tensor product of with any morphism. So that's what is a tensor ideal, and the first lemma is that negligible morphisms form a tensor ideal. So I will not prove this lemma, it is a kind of straightforward verification. And so the next lemma is the following, that let me assume that every nilpotent endomorphism in C has 0 trace. This is not necessarily true. This may fail, and maybe we will see an example. But it is definitely true for any symmetric tensor category, which is abelian, because in that case, you can, for such a endomorphism, take a filtration by kernels of its powers, and it is strictly upper triangular with respect to this filtration. So the trace, which only depends on the diagonal part, is 0. And more generally, if C admits a monoidal functor into an abelian symmetric tensor category, then it is still true because trace commutes with monoidal functors and can be computed after applying this functor. So suppose we have this proper trace 0 property, and then the lemma says that the quotient C mod n, which we call C bar, is a semi-simple symmetric tensor category. So what do we mean by this quotient C bar? The objects are the same as those of C, but morphisms home in C bar from X to Y is the morphisms in the old category home C from X to Y modulo this subspace N of X, Y. So you can define such a quotient for any tensor ideal, but the claim is that when we have this trace zero condition, then the resulting category will be a symmetric tensor category, an abelian one, and moreover a semi-simple one, which means that it will have complete reducibility. And the next lemma, which was proved many years ago by Benson in the setting of modular representations, gives an explicit description of this category C bar, which in particular allows us to see that it is semi-simple. So under the assumption of zero trace, the following hold. First of all, part one is a characterization of negligible morphisms between indecomposable objects, X and Y. Actually, it's easier to say what it means for it to be non-negligible. So it says that it's equivalent to being an isomorphism and dimension of X, categorical dimension of X, not zero. So F is not negligible if and only if it's an isomorphism and dimension of X is not zero. So basically, what does this thing say? So if X and Y are not isomorphic, then every morphism between them is negligible. And if X and Y are isomorphic, well, we then can assume that Y equals to X. So we have a morphism from X to X. So the ring of morphisms from X to X is a local algebra, local finite dimensional K algebra, which has therefore a maximal ideal M, and it is equal to K plus M. And then elements of M are nilpotent and therefore they are always negligible. But the identity morphism which remains may or may not be negligible depending on whether the dimension is zero or not. If the dimension is zero, it is negligible. And if dimension is not zero, it is not. And the second part says that how to tell if a morphism between decomposable, possibly decomposable objects is negligible. And that's if and only if all matrix elements, so if you have an object direct sum of xi and have a map to direct sum of yj with the matrix entries, block matrix entries fij, then this is negligible if and only if every single block fij is negligible. So now this category C bar, which we obtained by taking this quotient, is called the semi-simplification of C. And we obtain a corollary that simple objects of this category C bar are the indecomposables of C of non-zero dimension. So, so what happens? So this is by doing this quotientic, we basically force Schur's lemma on our category. So if X and Y are indecomposables which are not isomorphic, then all morphisms between them become zero in the quotient, so they don't talk to each other. And if they are isomorphic, then well, the only morphism that will remain is the identity and its multiples, or maybe nothing if the dimension of this object is zero. In that case, all morphisms from X to itself will be zero, including the identity morphism. And that means that this object X will become zero, will die when passing to the semi-simplification. So in other words, what happens is indecomposables of C become irreducibles or simples of C bar, but some of them become zero, namely those who had dimension 0. So I will give an example now. I will take category C, which is just representations of Z mod P, where K has characteristic P. So this means that we have an operator G on our vector space whose P's power is 1. And in characteristic P, this equation can be rewritten as G minus 1 to the P equals 0. So this means that G minus 1 is a direct sum of Jordan blocks of size 1 through P. So indecomposables are these Jordan blocks, J1, J2, up to JP. And J1 is the unit object, the trivial representation. Now, when we do semi-simplification, these become simple objects of our category C bar, which is L1 and so on, LP minus 1. And JP becomes 0 because its dimension is divisible by P. Hence, its categorical dimension is 0. So we will have P minus 1 indecomposables in this semi-simplified category. And then we can compute the tensor product of these L's, the fusion rule, and that turns out to be the Verlinde rule for SL2 at a root of unity of order 2p. More precisely, the usual Klebsch-Gordon rule. So Jordan blocks in characteristic 0 tensor the same way as representations of SL2 by the Klebsch-Gordon rule, which is this rule, but without these terms here. But when we do this semi-simplification, what happens is that this Klebsch-Gordon rule gets truncated. And instead of minimum mn here, we've got minimum of mn, p minus m, and p minus n. And for this reason, we call this category the Verlinde category, even though it was introduced maybe for more general, as a special case of more general construction by Sergei Gelfand and David Kashdan, independently Georgiev and Mathieu at the beginning of 1990s, about 30 years ago. And I will denote this category by ver P. Now, there is a variant of this construction which is very similar when you replace Z mod P by alpha P, which is the Frobenius kernel of the additive group. And so, examples, well, ver2 is just the category of vector spaces because it only has the object L1 in decomposable. ver3 has L1 and L2, and this tensor product rule says that L2 tensor L2 equals to L1. So it looks like it's Z mod 2 graded vector spaces or representations of Z mod 2 over a field of characteristic 3. But actually, one can see easily that the braiding, the permutation morphism on L2 tensor L2 has a minus sign. And so this is the category of supervector spaces over K. In general, this category ver P has two subcategories. One is spanned by odd dimensional LIs, and the other is spanned by L1 and LP minus 1 when P is bigger than 2. And ver P is just an external tensor product of them. And in particular, ver 5 is a product of these two things. And if we take x equals to L3, so ver 5 plus is spanned by 1 and x, and x tensor x equals to 1 plus x. That's very similar and closely related to the example we already discussed. So if you tensor x many n times with itself and look at the multiplicities, those will be consecutive of 1 and x. Those will be consecutive Fibonacci numbers, which is why this category ver5 plus is called the Fibonacci category. But it's a Fibonacci category in characteristic 5, while many people consider it's lift to characteristic 0, which arises in many subjects such as conformal field theory, subfactors, quantum computation, and so on. But here we're talking about the reduction of that category modulo 5. And that category is symmetric. So this category doesn't admit a lift. This category is Ver-P. They have the same fusion rules as the categories, Verlinde categories arising in conformal field theory, but they are symmetric, while the categories in characteristic 0 are braided, non-symmetric. So these categories do not have a braided, do not have a symmetric lift to characteristic 0 by the Lynch theorem, but they have a lift which is braided. But anyway, I should explain why this category Ver5 is a counterexample to the Lynch theorem in characteristic 5. So this tensor product rule means that if we had a monoidal functor from this category to some vector space or super vector spaces, then the dimension of the image of x would have to satisfy this equation, t squared equals to d plus 1. But there is no integer satisfying this equation. And that proves that this is a counterexample to the Lynch theorem. And in fact, for any p bigger or equal to 5, you can have do a similar calculation and show that there is no fiber functor from Ver-P. So these are genuinely new examples, which are not covered by super Tanakian categories. I should mention that the way this category arose in the work of Gelfand and Kazhdan and Georgiev and Mathieu was slightly different. They considered instead the category of tilting modules for SL2K, and took this category is not abelian, but it satisfies our condition. Namely, it has a trace 0 condition because it's a subcategory of representations of SL2K. And the semi-simplification of this category is Ver-P. So now the question is, how can you fix the Lynch theorem? So remember, we started with group representations, and then we had the notion of Tanakian category, which are categories that have a fiber functor to vector spaces, or are category of representations of a affine group scheme. And we could have asked ourselves at that point whether there is anything new, let's say with the moderate growth condition. And the answer would be yes, because there would be category of super vector spaces that is not of that type. And once we found that, there are many more examples, which are categories that fiber over that category. Namely, category of representations of affine supergroup schemes or super Tanakian. So now in characteristic 0, there is no more examples, as long as you are willing to assume moderate growth. But in characteristic P, we have found a new example, at least when P is greater or equal to 5. In fact, such examples exist they exist for every P, but we have found them for P greater or equal to 5. So since this category doesn't have a fiber functor, maybe we should do the same as we did with super vector spaces, which allowed it as a target for fiber functors. So we consider more general fiber functors, which take values in this category that we weren't able to construct from the previous setting. And so then we can ask if any tensor category, symmetric tensor category of moderate growth over K, fibers over ver P. Victor Ostrich conjectured that in 2015, and he proved this for fusion categories, which means under the assumption that it has finitely many simple objects and semi-simple. So if you have he proved that if you have a fusion category which has finitely many simple objects and is semi-simple, then there exists a fiber functor from C to ver P. That was a remarkable result because in this case you can consider the group scheme of automorphisms of F of this fiber functor denoted by F. And that's a fine group scheme internal to the category ver P. And our category becomes the category of representations of this G, compatible with the action of fundamental group. So this is a kind of detail that's not so important, so I'm not going to explain. So in other words, study of fusion categories over K reduces in this way to studying affine group schemes, in fact, finite group schemes with linearly reductive finite group schemes in ver P. Of course, there is a question of what they look like, and we now have a conjecture about that. But in any case, it makes the problem much more concrete because it reduces to developing Lie theory inside ver P. But then there is a question of what can we say about categories which aren't fusion. There is a simple counterexample for finite but non-semi-simple categories, which comes from a paper of my former student Siddharth Venkatesh. And this is the following. We just take Hopf algebra K of D over D squared, where characteristic of K is 2. So this is so we have a primitive element D. So this is just the group algebra of the Frobenius kernel alpha 2. That's definitely a Tannakian category, but we can consider a weird symmetric braiding, which is the composition of the ordinary flip with an R matrix. And the R matrix is going to be 1 tensor 1 plus D tensor D. So that's a triangular Hopf algebra. And then one can show that the category of modules over this triangular Hopf algebra is it is not a Tannakian category, and it doesn't admit a fiber functor into ver P, because ver 2 is the category of vector space. And in fact, with Benson and Ostrich, we were able to construct counterexamples for every prime, but they're more complicated. So then you may ask what prevents this category from having a fiber functor to vector spaces, which is the same as ver 2. And the answer is it's the Frobenius functor. So if you have a symmetric tensor category in characteristic 2, then you can define a remarkable functor in this category, which is called the Frobenius functor. Frobenius twist functor. And it's very simple. You take X, you take the tensor product of X with itself, and then we have an endomorphisms 1 plus P in X tensor X, where P is the permutation, is the symmetric braiding. Maybe I should call it C. Better to call it C, I think. This is what I called it before. And then c squared is 1. So this means that 1 plus c squared is 0 in characteristic 2. So we can view it as a differential from x tensor x to itself. And we can take its cohomology, which is the kernel of 1 plus c modular image of 1 plus c. So basically, you can, this x tensor x has a filtration with canonical filtration with 3 pieces. You have wedge 2 of x, x1, and wedge 2 of x. And this is the symmetric square, and this is the divided power square. And this middle piece is this Frobenius of x. Because the kernel of 1 plus s is this gamma 2x, and the image of 1 plus s is wedge 2 of x, so the quotient is exactly this x. And then there is an exercise that if you take the regular representation of this Hopf algebra here, and you take its Frobenius functor, then you actually get 0. While Frobenius functor of the trivial object, identity object, is always the identity itself. So we have a short exact sequence 0, 1, h1, 0. But when we apply to this sequence the Frobenius functor, we obtain a sequence that isn't exact. In fact, it's not left exact or right exact. It's only exact in the middle. So this functor isn't exact on any side. But on the other hand, it's an additive functor. One can show that it preserves direct sum. So on every semi-simple category, it would be exact. And also it commutes with tensor functor. So this means that if we had a functor, fiber functor, to vector spaces, we would get a contradiction. So this shows that this is an obstruction. Having a non-exact Frobenius functor is an obstruction for C to have a fiber functor to vector spaces, or to and there is a similar story for arbitrary prime. We take an object. So how do you define Frobenius functor there? You take x, you raise it to power p. There is a cyclic permutation acting here. C to the p equals to 1. Then we can view this x to the p as an object of C tensored with representations of z mod p. And then one can do semi-simplification, which will turn this into ver p. Don't touch the first factor. There is a way to do it so that you don't touch the first factor and only simply semi-simplify this factor, and then you end up in C tensored with ver p. So you get a monoidal functor from C to C cross ver p, which is twisted linear, so it raises scalar to pth power. And then this functor can be decomposed into a direct sum of objects of ver p with some multiplicity functors. And in fact, these functors can be described in terms of linear algebra. So in terms of filtration of x to the p by kernels of powers of 1 minus c to the I. So more precisely, for I is the kernel of A intersect with the image of A to the I minus 1 over the kernel of A intersect with image of A to the I, where A is this 1 minus C. And now the definition says that C is called Frobenius exact if this functor is exact. And the main theorem that we proved that's the only obstruction. So if our category is Frobenius exact, then it does have a fiber functor into Verlinde category, and moreover, this functor is unique. So that's a generalization of the Linz theorem to positive characteristic. Unfortunately, it is not yet the whole story, because this rules out this non-Frobenius exact category, which I explained before in characteristic 2. and many other interesting examples. But at least in the case when our category is Frobenius exact, this is true. And the important special case is when the category is semi-simple. So any semi-simple symmetric tensor category is Frobenius exact by definition, and therefore admits a fiber functor interval P. This is what Ostrich conjectured in 2015, and we proved 6 years later. So the proof is quite complicated. It combines the methods of Deligne with the new methods that were developed by our author, Kevin Coulombier. So now I will explain how this theorem can be used to prove the classical result that I started my talk with, and that will be the last thing I'll do. Any questions?
No, that's the same question.
Okay, so let's then explain. So remember the setup. So we have a category of representations of a group G. And so let us take its semi-simplification, C bar, which is going to be called, so that's a semi-simplification of the representation category of G. And then remember we had this dn of x, and dn of x was the number of non-negligible summands in x to the n. Now, what will happen to this when we take semi-simplification? Remember that indecomposables become irreducibles except those of dimension divisible by p. So this procedure will kill exactly those that we ignored, which are negligible ones, and make the other ones into simple, so irreducibles. So dn of x will simply be length of x bar to the n, where x bar is the image of x in C bar. So I said that the objects don't change, but when I regard x as an object of C bar, I will call it x bar to distinguish. Now, our main theorem says that this category rep K of G bar, since it is semi-simple, admits a fiber functor into ver P. In other words, it's a category of representations of some affine group scheme in ver P, which is linearly reductive. Now, we can compute this length before or after the functor f. And in fact, they're not the same, because functor f of a simple object may decompose and become semi-simple and not simple. However, one can show that this length does not increase too much when we do that. In other words, although root of degree n of length of x to the n bar is less than or equal than the root of degree n of length of f of x bar to the n, it is not much less, in the sense that they go to the same limit. In other words, the factor by which the length increases when we apply the functor f is a sub-exponential function of n. It grows slower than any exponential function of n. And as a result, these things have the same limit. And this implies that this d of and some object y can be computed as the limit of, so d of x can be computed as well, all right, I call it y. Frobenius, so it is the length of the tensor power of f of x bar, where f lands in this Verlinde category. But this is a very simple problem, because in this category, we have finitely many simple objects, and f of x bar just multiplies them by a certain matrix. And then we know, basically, we're down to the problem of computing asymptotics of matrix entries of a power of a matrix. And that is governed, of course, by the spectral radius of this matrix, which is called the Frobenius-Perron dimension of this f of y. So we have concluded that this gross dimension of a representation d of y, which was our mysterious real number, is in fact the Frobenius-Perron dimension of f of y bar of this thing in the semi-simplification. And in particular, it is already clear that this is an algebraic integer, because it's the largest eigenvalue of a matrix with integer entries. But in fact, we can do better than that, because we know that this f of y bar is a direct sum of simple objects Li of our Verlinde category with some multiplicities Mi. And therefore, this d of y is going to be the sum of Mi times the Frobenius-Perron dimensions of Li, which are just q analogues of I. And we get this formula that this is the sum of Mi times Iq, which is exactly the claim that I made at the beginning of the talk. So any questions?
No.
Hi, can you hear me?
Yes.
So does this imply that this is a character from the Grothendieck ring? I'm not quite sure.
Yes, exactly. It implies that, because for finite, for fusion categories, this gross dimension is well known to be a character. If you have a fusion ring with finitely many, with finitely many objects, you get matrices, and the largest eigenvalues are additive and multiplicative on those positive matrices.
Okay, I see.
Other questions?
Can I ask a question about the main theorem?
Yes.
The main theorem. Do you have to have some kind of special treatment for p equals 2 and maybe p equals 3 in that proof, or is it fairly kind of?
No. There is no special treatment. It is exactly the same proof. And what this shows is that in characteristic 2 and 3, actually, Deligne's theorem is true on the nose for Frobenius exact categories. And the dimensions we get are always integers for that reason.
Thanks.
Other questions? Yeah, so maybe I'll finish with a few comments that we get a few corollaries from this. So one corollary is that if you take a representation of a modular representation of a finite group, then we can, well, when you tensor this representation with itself and with its dual, the indecomposable summands can get very large. However, they cannot get very large in the sense of this gross dimension. Namely, the gross dimension of any summand in such tensor product is bounded by some constant which depends only on x. And in fact, it depends only on So in fact, it depends. It's less than or equal than I think a constant times p to the power d of x, something like this. And this is so let me explain how this works in characteristic 2 for simplicity. So in this case, we have this semi-simplification is well, I mean, it has a fiber, it's a Tanakian category by our theorem. So it has it's a representation category of some linearly reductive affine group scheme, G bar. It's in general a scheme of infinite type, because for very simple groups such as Z2 cross Z2 cross Z2, it's already a wild problem to classify indecomposable. So there are lots and lots and lots of them. And this category isn't going to be finitely generated. So the group scheme G bar is going to be in inverse limit of group schemes of finite type. So it's going to be some huge mess, but it does exist. And well, if you want to be less messy, we can take an object X there and look only at the subcategory generated by this object. And that is a representation category of actually some group scheme of finite type, linearly reductive. And we know a classification of such group schemes. This is due to Nagata. It's a famous theorem of Nagata, which says that if you have a linearly reductive affine group scheme of finite type, which means that its representation category is semi-simple, then actually it has the following structure in characteristic 2. It has a normal subgroup, which is abelian, and which is a product of a torus with the dual to a finite abelian 2 group. And then a quotient, the quotient is a finite group of odd order, which, by the way, is always solvable by a theorem of Veit and Thompson. And so representations of such group, irreducible representations of such a group, always have an eigenvector for this abelian subgroup, and therefore their dimension is at most the order of gamma. And so this mx actually can be taken to be the order of gamma. Now, Benson conjectured the following, that if G is in fact a 2 group, not just a finite group, but a group of order which is a power of 2, then this gamma is always trivial. So then this would mean that the growth dimension of every indecomposable is 1 if it has odd dimension. So in other words, if you have an odd dimensional indecomposable, then X tensor X dual contains K as a direct summand, but all the other summands have even dimension. And in fact, even they have dimension divisible by 4. So the statement that it has even dimension, which is the weak form of Benson's conjecture, is the statement that this group gamma equals 1. But we're unfortunately very far from proving that at the moment, even though there is a lot of computational evidence. Our theorem only implies that there is a finite group gamma here, but so which gives a bound on the dimensions, like I said, but we are still far, and this group may be non-trivial. For example, if you start with a group gamma, you will get the same group gamma. But if your initial group has order a power of 2, then the conjecture is that this gamma is trivial, which is this elementary property of representations. Unfortunately, we don't have any idea how to prove this. Okay, thank you very much.
Thanks, Pavel, for the great talk. It's you have a very strong result. Let me just stop recording.